Hello everyone, welcome back to Random Matrix Theory. This is lecture 09. So today we'll study the basics of matrix models. So in case of matrix models, the basic field, or in a more layman's term, the basic variable, are matrices. So basic field or variable matrices. Your matrix integral is a proof of how things work in the matrix model arena. So we can consider in the matrix integral, we can consider potentials of the form, let's say over GS is Wm is our potential, is trace of m squared plus GS, let's say p greater than equal to 3 GP over p trace of m to the p. So there are various things to discuss here. For example, GS, GP are our coupling constants. And previously we had the coupling constants in, say, in the numerator. For example, we had, if we were considering say tetravalent vertices, we had like this. So these are basically constants, so you can write them in any way we want. And in this notation, you have the freedom to just write the coupling constant as a denominator. So this is a general form of our potential, that is a Gaussian potential plus some anharmonic term or some term, which is this. And if you remember, you considered in your exams or while solving problems, we considered trace of m cubed, trace of m4, trace of m5. This is a more general form. This generalizes to any power of m, trace over any power of m. Okay. The partition function of this matrix model theory is given by I'll explain this in a bit, and the integration is over matrices. Since it's a matrix integral, it looks something like this. So this is like before, if you remember, we normalized our matrix integral. This is sort of like the normalization factor, and for those who have some bit of familiarity with quantum field theory, in physics it's written as the volume of a gauge group. So that's why the volume, for us, it is just a normalization factor, and I'll show how we get this factor. Previously we just normalized with 1 over z, that is with the Gaussian part, but this has a more general interpretation, so we'll discuss that when we go to the, basically they are discussed when we are dealing in the eigenvalue basis, that is when we have turned our matrix integral in the eigenvalue basis. For now, consider this as a normalization factor. Also, the partition function of matrix models, say for arbitrary p, if you remember, how do we do it? We expand or do perturbation theory, that is expansion of this term. You have done it by doing then sometimes called the perturbation theory. We expand in terms of the coupling and around the Gaussian point. In a more so this means that if you remember, if you had a matrix integral like this, let's say half gs trace of m squared plus, let's say, g3 gs trace m cube. So if you expand this, what do I mean by doing perturbation theory? It's just if you remember this is basically doing perturbation theory. G3 gs trace of m cube and so on. This is basically what I mean by doing perturbation theory around the Gaussian point. Example. Okay. So after doing perturbation theory, we can compute the partition function as a power series in the coupling, as the coupling, in terms of the coupling. So we can write it in terms of power series, as we have seen, and we can compute the partition function, and as you have done. So the interesting thing is, these matrix models can be interpreted in terms of graphs, or in a physics language, physicists call it Feynman diagrams. So you have seen at the start of our course, we did draw a line between Gaussian integrals and graph symmetries for one-dimensional case, two-dimensional case. There's a one-to-one correspondence there. This kind of a duality there. So this kind of matrix integrals generates graphs. In a similar fashion, these matrix integrals, they were one variable ones. Now we have matrix integrals. They also generate graphs, which we call fat graphs or ribbon graphs. And if you remember, the free energy can be written in terms of, previously we wrote free energy like this. Let's give it. Free energy can be written like this. That is, it generates all connected diagrams, or connected diagrams, or in other words, we might call them vacuum bubbles. So these are different names for the same thing. They are just connected diagrams. Okay, so this is the free energy. And now let's talk about the kinetic part. The kinetic part of the theory is of the form sometimes we call this the kinetic part. It's because it's, when in a more physics language, it's sort of like, if you have done classical mechanics, this is sort of like the kinetic energy of a Hamiltonian or of a system you're considering. So it's sort of like a kinetic term. And so the Gaussian part is sometimes called the kinetic term. So it's just the trace which is mji. And if you remember, propagator of the theory is mij mkl gs delta il delta jk. There are various notations of, or various ways to write these things up. In the notation we are following, this involves a coupling, but in, say, other notations that we did before, there wasn't any coupling. The idea is to get used to the notations because they mean the same thing. If you think about it, they're basically the same. The notations don't mean anything. And a reminder that for one variable, this was like xi. The propagator looked something like this, and xi xj was equal to the inverse. It was something like this. So the propagator of the theory of matrix models can be represented, or is represented, in double line notation as il, right? Let's go down. It's the notation is, it's going into one of them and going, it's sort of like a loop. il delta jk. So now consider our favorite example, the trivalent vertex. The first one, trivalent vertex, that is p equals 3. So if you remember, the different powers of this trace, the different, where did I write up? The different powers here correspond to, different powers here correspond to different, say, valency, right? Whatever, let's say if I'm dealing with trace of m cubed, I mean I'm dealing with graphs of valency 3, trace of m4, graphs of valency 4, and so on. So now consider the trivalent vertex, and let's trace over m cubed, and you can write it like this, and it's basically a sum over ijk mij mjk mki. This is basically the trace. So any vertex of order p, so, is basically the number of double lines going out of the vertex. For example, in 3 it would be something, I'll draw it in a bit. So it's basically the number of double lines going out of it, and it can be represented by drawing p double lines joined together. So for order p, so the rule is for order p, which is, say, vertex of order p, it means, the order means the number of double lines going out, or the valency. So the valent 3 graphs. So vertex of order p can be represented by drawing p double lines joined together at the vertex. So if we draw it, Let me draw the figure first. So if we give it I, let's say this is my j, I, j, k, k. So it's going out, so this should go in and this should go out like this. So this is a cubic vertex in double, let's write like this, double line notation. So the corresponding graphs that we get from this type of integrals are called ribbon graphs or fat graphs. That is because they have a different structure compared to our single line graphs. So they are sometimes called fat graphs, ribbon graphs, fat Feynman graphs, depending on what perspective you're looking at from, and the notation of the person writing the book. So now let's consider two cubic vertices. Two cubic vertices, which is, if you remember, for two cubic vertices, in case of single line graphs, this would just be like this. Let's say single line graphs or simple graphs, which are in fat graphs. So two cubic vertices correspond to this, and let's see how things span out in double line notation. Matrix models. So how will it span out? If you write it down here, MJ, K, L, M. Okay, there are four of them gone. N, N, I. 1, 2, 3, 4, 5, 6. Yeah. So if you do it, your answer will be some number. This number will depends on symmetry, the symmetries of the graph, and number of graphs and number of graphs. So I'm not explicitly showing it, I'm just looking at what's happening, and some number n. So if you do the expansion, or if you calculate the C in the two vertex scenario of the matrix models, two cubic vertices, you'll get something like this. And a good thing to remember is our I, J, K, L, or whatever, the indices, alphabets, run from 1 to n. You can show it by yourself that you'll get this. So the things you have to use is Wix theorem, which I showed you previously. So using Wix theorem and our expression for the propagator, is this. Using Wix theorem and our expression for the propagator, you can easily arrive at this. You just have to pair them up. You'll have three terms, add them up, and so sorry, you won't have three terms. You'll have around 5. Okay, you just have to use Wix theorem. Just pair them, try pairing them up. You'll get the number of pairs, and if you use Wix theorem, you'll arrive at this. Just use the propagator and you're done. So after you arrive at this, these two terms corresponds to two different diagrams. Previously, in single line, it was a single diagram, but in our double line or matrix model scenario, there are two diagrams. The first diagram, the Wix theorem, this should be 2n minus 1 double factorial terms, so yeah, I remember it. So you'll get the required terms from that. So from the first diagram, that is, which would correspond to this person, this diagram would be, let me draw it. This is my cubic vertex. Let's try it. So one of them, and the third one. This is your cubic vertex. You have two of them, and they join like this. So the power of n tells you how many faces or how many holes you have in your fat graph. So how many holes do you have? 1, 2, 3. So this comes from the propagators, and since you have a cubic vertex. So yeah, the second diagram is, let's draw this. Yeah. There are very better ways to draw it, but I'm very bad at drawing these things. So yeah. So these diagrams are like this. Just this contracts with this, this with this. Let me draw it closer. This one with this one, and this one with this one. So what you have is something like this, a graph like this, where you only have one face. If you look at it, there is only one face, that is n. Yeah, that is G, or one hole in it, because the overlapping thing might be confusing, because let me try to see if I can draw it better. Let's see if I can draw it better. So goes like this, goes like this, yes, goes like this, it goes underneath it, goes like this, goes underneath it. So there's basically one face or one hole. So the power of n tells you the number of holes you have. So, but when you're doing this, when you're giving this a topological analysis, then it tells you the number of holes. But in general, from Wix theorem, if you do Wix theorem, you will get these, and these two corresponds to these two diagrams. So in general, fat graphs or ribbon graphs, fat graphs are characterized topologically by the number of propagators or edges, that is the number of lines coming out, or that is the number of lines that go in and connects with the other, that's the edges or propagators, vertices V, and closed loops or faces H. So if you are, this V is just a sum of, since we have VP here, it's just sum of all vertices VP. So if V can be written like this as well. So V is the total number of vertices, not any specific vertex. For example, if you're looking at two vertices, so it's the total number of vertices in a certain expansion, or if you're doing a matrix integral expansion, that is. So this V is the total number of vertices, not a specific vertex or something. So now each fat graph, so fat graphs will give a factor of, let's say GS. Of course, it comes from the propagators. Each propagators give you, if you remember, MM, it gives you GS and some deltas. So the propagators give you GS. So if you have E propagators, the power of GS should be E, right? Edges E. So each fat graph will have GS to the E, and the easiest one is this, the number of holes or faces, and it's very easy. Here we had 3 faces and here 1. This one is very easy. And each vertex, if you remember, our vertices were something like this, GP by GS. So each vertex will give me, so we'll have GP to the V and GS to the V, right? Because that's the number of vertices you're looking at, right? So in case of the fat graph, here you had 2 vertices. So each fat graph ultimately gives me like E minus V, because it comes from each vertex, each interaction vertex. That is, here you had 2 interaction vertices, so E minus V, and in a more formal tone, this is written like this, GP to the VP. It's in a more formal tone, it's written like this. And yeah, so each fat graph will give me a factor like this. How does it come? Propagators give you a factor of GS, so, and interaction vertices give you GP over P, and it's V of them, and N to the power of H is the number of faces or holes. Okay, so the key point is here, key point, or say important observation, important thing in this theories or in this analysis is fat graphs are considered as surfaces with holes. That is, it can be considered as Riemann surfaces. These are basically surfaces that these Riemann surfaces are basically surfaces that mostly you see in real life. Of course, there are exceptions, but for those who aren't familiar with it, these are the surfaces that you see. For example, let's say your paper is a Riemann surface. So the sphere is a Riemann surface. And let's see, what examples do you have? The torus is a Riemann surface, or things with handles. So fat graphs can be viewed as Riemann surfaces with holes, or say faces. That is, they can be given a topological analysis we can give a topological analysis by considering fat graphs as Riemann surfaces. And as Riemann surfaces, they are, for those who have a bit of familiarity in this context, Riemann surfaces are orientable to manifolds, and they are classified by the genus. So in case of fat graphs, we'll treat them as Riemann surfaces, and we'll give them a classification in terms of the genus of the surface. So ideally, fat graphs will consider them as surfaces with certain genus. Genus is basically the whole, and so okay, let's write it like this. So each closed loop, one more thing before we go to the topological analysis, each closed loop represents the boundary of a hole. It's good to remember that, of a hole. So closed loop here, it's a boundary of a hole. Here same, here same. So if you have a closed loop, here you have only one closed loop, so one hole. Okay, so now genus of a surface is determined by the elementary topological relation two G minus 2. It's for orientable Riemann surfaces, of course. So if you know a bit on orientable Riemann surfaces, is surfaces that are orientable. Non-orientable is those who have seen Endgame, Avengers Endgame. That's Mobius strip, right? They draw something that non-orientable are if you go around the whole surface, and if you end up directly opposite to the surface, then that's a non-orientable. For an orientable one, if you go all around the surface, you should return to the same point. So if you return to the opposite point, that's non-orientable. Okay, so using this, we can use this here for here. Okay, so we have everything in terms of the genus. So let's use this, and we can write GS using this. This E minus V, I can take the H on that side, so GS will have 2G minus 2 plus H, N will have H, and P G C VP. Okay, so sometimes it's written like this. I'll explain a bit what T is. T is here. T is equal to NGS. Sometimes it's considered like that. So it's called the Tuft parameter. Sometimes, in almost all of the times you just write it in terms of the Tuft parameter, and the Tuft parameter is just N times GS. So you consider a new parameter, and in some literatures, it's the Tuft parameter is, instead of T we use lambda. So if you are reading any textbooks, if you see lambda to the H, you know that's the Tuft parameter. So these, so now fat graphs, let's say a thing or two about the fat graphs before we end the video. Fat graphs with g equal to 0 are called planar graphs. That is, the genus is 0, that's a planar graph. Genus greater than 0, non-planar graph. So now let's see our first and second diagrams that we draw. Okay, sorry for the disturbance. First and second diagram. So let's go back to our first and second diagram and see if they're planar or non-planar. So this one, how many edges or how many propagator? 3, right? 1, 2, 3. 3 of them connect with the other. Same for here. How many vertices? Of course, we are in the second vertex scenario. We're considering expansion at the second vertex, interaction at vertex of order 2. So you have 2 vertices. How many holes? Here we have 3, here we have 1. So now let's use this topological relationship and let's find out. So you have edges 3, vertices 2, holes 3, vertices 2, holes 1. So now let's use vertices minus holes, and if you do it, that's okay. 3 minus 2 minus 3, so it's minus 2. If you take the 2 that side, it's genus 0. Similarly, just minus vertices minus holes, 3 minus 2 minus 1. If you do it, it's genus 1. So the second diagram is not planar. This is planar diagram, that is, this is non-planar. So these fat graphs are often regarded as Riemann surfaces. So if I regard them as Riemann surfaces, this is a Riemann surface. This fat graph, the first one, is a Riemann surface of genus 0. So they are topologically equivalent to a sphere, right? Or yeah. And the second diagram is a fat graph of genus 1. So they're topologically equivalent to a torus with 1 hole, right? So when I say I'm regarding them as Riemann surfaces, the advantage that I get is I know which fat graph is of a certain genus. And if I say, for example, when we were talking about two-dimensional surface, covering a two-dimensional surface with planar diagrams, we can cover a 2D surface with no holes. With g equal to 1, we can cover the two-dimensional surface with 1 hole, or one with genus 1 with non-planar ones, or fat graphs which correspond to genus 1. So this is the main reason of giving them a topological analysis. One of the reasons.